Let's go ahead and we'll draw, so the idea here in, do you remember this notation, the star x 1 0 notation? So we've got an A that just has a bunch of elements. We're not really sure what those elements look like. What did x's mean again? Yeah, we could call that the time. It's not really an x like a variable. It's just like a time symbol, right? And then the claim is we will now factorize this thing. One of the factors will be the factor L, and the other factor will be the factor U. What does L look like? L has, not only does L have non-zero strictly lower triangular elements, but L has what type of diagonals? All ones. That's why we call it unit, right? And that one's a little bit more clear, right, Kush? Why we would call that unit lower triangular? Yeah. That one makes me smile. The regular one like makes me go like, that same reaction you had, I have like, it's strange, you know, like, what's irregular then? Yeah. What about U? So when we think about the sparsity structure of U, what does that look like? Yeah, not ones on the main diagonals, but just what can't be true? Non-zero. And do you remember which of these sparsity structure notations we use for non-zeros? Stars, you got it. Star. And then this is kind of a useful thing. This is one time I actually don't mind doing this. When talking about sparsity structure, right? And sometimes I would actually leave it like this. Later in your life, if you were to actually work in this field professionally, you would start getting into the idea that when you do these calculations, you actually store this in the same matrix. You overwrite it. So the upper triangular portion is stored here, and then this portion is stored down there, so you don't have to use extra memory, but that's called computer science, right? There's a lot of really cool stuff that goes into algorithm creation here, but we won't talk about that this quarter.